Hi, in the spaceflight lecture series now, we are in the last leg of the spaceflight mechanics understanding, wherein we are now going to look at some very important concepts of orbital mechanics, right? Wherein the most important focus is going to be about one, the mechanics itself, two, something called as inter-orbit transfer, and then three is multi-stage rockets or something called as staging. Now, these 3 points are very important in the journey of spaceflight mechanics simply because they form the final pinnacle of all the theoretical understanding we have gathered so far, right? So far if you have seen our journey of how we looked at the gravitational variations, we looked at the satellite maneuvers, we looked at the energies, right? We looked at gravitational potential and eccentricity, the theory of conic sections and so on and so forth, right? We are now in a point where we have to look at a lot of detailed thinking about satellite and then orbital maneuvers, right? And in order to do so, we are going to first focus now on these 2 points, that is orbital mechanics and inter-orbit transfers. Now, we have already seen that a satellite which you have seen has an orbit of certain eccentricity, right? So for example, we had seen that a particular orbit has a semi-major and semi-minor axis and a set of conical sections, right? The conical sections would be about saying what sections would come into which picture and so on, right? Let's recap some of the definitions and terms that we had looked at because those are very important, right? The first is about semi-major axis, right? We had seen that in elliptical orbit, the axis that is formed is this, right? And this is the center, this is the semi-major axis, this is the point of foci, right? And with respect to one focus where Earth would lie, you would see the entire mechanics, right? Then you had semi-minor axis, which was B, correct? One important thing after this we have to look at is inclination of the orbit. So this is the orbit. This theory we are very clear. But now we are going to use a demonstration of these smiley balls. This smiley ball represents my Earth. Okay? If you have seen this lining here, right? Earth is not a perfect sphere, but for theoretical aspects of undergraduate student learning, you can consider Earth to be perfectly spherical. Then on this Earth, if you see this, let's call it equatorial line. Okay? So if this is the ball that I place, right, the smiley ball, this is the equatorial line, correct? Let's imagine our India is somewhere here in the northern hemisphere. You launch a satellite in this plane which rotates, circle exactly parallel to this equator, right? So you would see actually a dot moving like this, correct? Then disappearing, again appearing. If you see from the top, you would see the smiley face of the Earth and a dot moving like this, correct? That's how you would see. This is called to be zero inclination. So plane that passes through this equator forms the basis for understanding what is happening to the satellite. Now, a plane which is at an angle, so this is the Earth's equatorial plane, right? This is the Earth's equator. A plane which is at an angle alpha with respect to this, a satellite will move something like this. Let's use 2 markers so that you are absolutely clear about this concept. This is Earth's equatorial plane. This is inclined plane. A satellite moving in this orbit, say, would move something like this. So how would it move? It would move like this. You see the angles? Up at certain angle, down at certain angle. It may be circular also, no problem. But it is at an angle with respect to this horizontal plane. This is called as inclination of the orbit. Okay? So orbital inclination is a very important concept because it talks about how the relative plane is oriented. Zero inclination is equator. Now, within this also, if this is my ball and Earth is rotating like this, right? How does Earth rotate? From west to east, right? From west to east. That's why you see sun rising east to west. Now, if Earth is rotating something like this, and my satellite also rotates in the same direction, right? Look at this face. So this is the direction of Earth's rotation and this is satellite direction. This is called as prograde. But if my satellite is moving in the direction counter-opposite to Earth, it is called retrograde. So prograde and retrograde are the two examples of relative difference between the direction of motion at zero inclination. Okay? So this is one important aspect. Second, 90-degree inclination, polar orbit. What does that mean? This is my Earth, happily rotating from west to east, and I am moving like this. What would it do? Say I am at top, exactly northern pole. As I keep moving like this, and my satellite keeps moving, see the coverage it is doing, right? So it will pass through a particular area continuously, covering the large area on the Earth, because it will form these strips, right? Because it is 90-degree velocities. So this will be the relative velocity. So the strip of the band on Earth here would be covered. So polar orbits are used for covering large area. Where are equatorial orbits used? If both the velocities are matched, you have, if omega of satellite is equal to omega of Earth, steady dot will appear, static. This is called geostationary. And if it is not same velocity but prograde or retrograde, it will be called geosynchronous. Geostationary, you will need an extreme special case of very high bandwidth, high intensity based communications. This you need most of the times for GPS based navigation, right? So that's the difference. Inclination of 180 degrees. Now what does 180 degree inclination mean? 0 is this, 180 is opposite direction. So this is called as retrograde. So when the plane is this, Earth moving from west to east and you moving from east to west, 180 degree, right? In between are inclined orbits. Now there is one more thing called as argument of periapsis. Now periapsis is the nearest point, right? When it is Earth, perigee. When it is Sun, it is called perihelion. Helios is Sun, right? When it is Moon, perihelion. When it is Jupiter, perigeum, right? So that is how you use. Then you have time to periapsis, which means the time of periapsis passage is the time in which satellite moves through its point of periapsis. Longitude and ascending node. Now this is very important. This is the satellite, this is the Earth, and this is the equatorial plane. Right? The satellite is moving something like this. So it is going to cross this plane twice, going up, going down. See here, this is the plane, and my satellite is now moving like this. So it is going to cross my Earth's equatorial plane, this plane, at one point going up towards the north. This is called as ascending node. And this, when it crosses down, is descending node. These are easy to observe for celestial planets and objects, and these have the roots in astrophysics and astronomy. That's where this comes from, right? Then you have the longitude at which the ascending node is, because latitude is about vertical but longitude is horizontal, right? Then you have time period, how much time it takes, and then something called as true anomaly. True anomaly mu is nothing but this. So this is the foci from which the distances are measured. This is the true anomaly. So at any point P of distance r measured from this foci F1, which is Earth, this is my perigee, this is apogee, right? This is semi-minor axis. This distance r measured from this focal point P forms an angle mu with respect to semi-major axis. This is called true anomaly. Okay, and then we will see something called as mean anomaly also. So orbital mechanics resides on these certain definitions. Of the 6, the anomaly, the time period, the longitude of ascending node, right, inclination, perigee, and apogee. Of these 6 parameters that define the orbit, 3 are sufficient to define orbit fully. So 3 observations about these 3 parameters can tell you completely about all other parameters and define the orbit completely. This is a very powerful and subtle message. You need not know everything. Maybe you know time period, anomaly, and longitude of ascending node. From there you can construct what is the perigee, apogee, as well as inclination. Okay. So therefore, any 3 will suffice for remaining 3. That's the whole message. Now, in orbital mechanics, therefore, extremely important points to remember are geostationary orbits, where it appears to be steady because it is in equatorial plane. Geosynchronous, they are circular orbits having 24-hour time period. Okay. Polar orbits, 90-degree inclination we have seen. Molniya orbits, these are something very important. Molniya orbits have time period 12 hours, okay, and inclination I of 63.4 degree. So if this is the Earth, they will form inclination of 63.4 degree. So they will cross something like this. In this plane, they will form this orbit. Okay, this is the elliptical orbit that these satellites form at 63.4 degree inclination. Right? This is the plane. Right? You see this? So they are, with respect to this, at 63.4 degree, like this. But the most important point is, apogee is in northern hemisphere and perigee is in southern hemisphere, very close. Why so? Any guesses? A landmass which is majority interest is maximum covered in northern hemisphere. Satellite slows down significantly as it moves towards apogee. So it will spend maximum time in this zone, almost 11 hours. So from crossing the equator, ascending node to descending node, it spends about 11 hours in northern hemisphere, giving you enough time with slower velocity to do your analysis and image capturing or any other navigational maneuver. That's why these are very popular orbits. Then you have walking orbits, right? These are used because of influence of sun and moon or other planetary systems. So for example, if you want to go from Earth to Mars, you will go through this walking orbit where other things are going to play a significant role in terms of your direction. Sun synchronous orbit, everything related to sun. And then you have parking orbits, wherein you park it, and as we will see in part 2, you use thrusters to then change the direction, right? Or change the velocity. So these parking orbits are intermediate orbits to form orbital transfers towards final orbit. Now we have seen a detailed derivation of perigee and apogee and the discussion so on and so forth, right? What we should do now is we should look at few more important concepts about angle node and foci of the satellite. So this is my satellite orbit, okay? This is perigee point with velocity Vp. This is apogee point with velocity Va. This is the foci point from which any point, let's say O, is measured. Okay, this is the local velocity direction, this is radius, this is r direction, and this forms mean anomaly angle mu, right? That's the true anomaly. Now if that is the case, right, and we know that this is A, E, this is A, correct? If that's the case, angular momentum which is conserved, H equal to V cross R, is radius into V perpendicular in this direction, which is omega square R. So R, if you do this, is H square upon Gm 1 plus E cos theta, right? If that is the case, V perpendicular would be Gm upon H 1 plus E cos theta, right? Is this clear? Theta is nothing but this anomaly angle that we have been using, right? Now the velocity parallel to the radius direction would be dr by dt, right? Which is d by dt of this h square upon gm. So h square upon gm 1 plus e cos theta whole square, right? This will be e sin theta d theta, because derivative of cos theta is minus, so minus minus becomes plus. So d theta by dt, right? But what is d theta by dt? It is omega r square. So which means I can simply write here V parallel is h square upon gm e sin theta into gm square upon h raised to 4 omega r square. So V parallel, after cancelling this, gives you gm upon h e sin theta, and then the tan of mu is 1 plus e cos theta upon e sin theta, right? Because what is tan of mu? V perpendicular upon V parallel. So to find out the anomaly of a moving point, you need to find the ratio of parallel to perpendicular velocity, right? Because this is the velocity, right? So one velocity is in this direction, one velocity is in this direction. This is the angle, right? So all you need is the tan of this angle, right? The tan of the angle here of this mu, and this is pi minus mu, is going to give you this, right? So basic trigonometry will tell you that mu is tan inverse of this, but you found out v perpendicular. So your anomaly mu, which is tan inverse of 1 plus e cos theta upon e sin theta, depends on the angle made by it with the foci, which is what you can measure, and the eccentricity of the orbit. That's it. Only two parameters. So this is the most important derivation and result, which you should understand very, very carefully, because it forms the basis of something called as true anomaly. Now, this anomaly mu that we have been trying to find depends on e cos theta sin theta, and it changes continuously, right? Because it is elliptical orbit. It moves, right? Let me get the ball again so that this orbit has a motion, right? So which means even if I am making inclination 0, the anomaly, because Earth is at one of the foci, right? Anomaly continuously changes as you moving on the orbit, which is something not great. So you do something called as true anomaly. What is this? You have first elliptical orbit, right? Let me take a different marker. In this elliptical orbit, you have this axis, right? You have this V perigee, right? At one of the foci, Earth is present. Let's say this is a point B, which forms an anomaly mu, right? This is the mean anomaly. Now, this is at a distance x and height y. So that equation of ellipse is x square upon a square plus y square upon b square equal to 1. That holds true, right? Now, the trick that I do is I take this point, okay, and this is very important. I draw a circle which circumscribes my ellipse, okay. I draw a hypothetical circle which circumscribes my ellipse. And what will be the radius of this circle? Radius of circle is A. So this circle, now I project this point here called as B dash, right? Or if I call this point to be P at a distance R vector, I call this point B. This forms certain angle E. E is called true anomaly. Elliptical orbit transformation into circular orbit is of extreme importance, because things in terms of velocity and angle come true, right? Because now omega of this hypothetical circular orbit gives me instantaneous anomaly at any point, or dE by dt directly becomes omega of circular orbit. So indirectly I want to transform my elliptical orbit into equivalent circular orbit, so that these relations in anomaly are simple, because the mean anomaly is what? 1 plus e cos theta by e sin theta, very, very difficult, tan inverse of that, continuously changing. Here it is a constant tau. Now this is E, right? Now this is not enough, because I need to find something about y. So now what I do? I draw a circle which inscribes the ellipse. Do you see now? So this is my ellipse. What will be the radius of this? B, right? So one circle circumscribes ellipse and one inscribes the ellipse, right? In this circle now, this point is projected with the same height to lie here. Then what will be my relation? The triangle that I will draw from here would be, this is r, this is pi minus mu, right? Because the anomaly is mu. This magnitude is y, right? And what is this magnitude? Since I know the anomaly, r cos pi minus v, right? And this is like, so this is a, I mean the equilateral, this is a triangle which has 90-degree angle in between. So you have y square plus r square cos square. Now cos of pi minus mu is minus cos mu, but in square it will simply be this is equal to r square, right? This is the first relation that I get by drawing this inscribed circle. Now I have to focus my attention here. Something which circumscribes x upon e. X upon e is what? Because e is this, right? That's why I have moved this arm like this to come here. This arm is moved. So this is e, right? The radius of circumcircle. So cos e is x upon e. And y by b. Now what is y? Y. Right? And what is b? B. So y by b is sine epsilon. Right? Are you able to clearly grasp this? Which means this together, sine square plus cos square is equal to 1, satisfies ellipse again. Now this is very easy. Only with this true anomaly E, I can define the circle. And that's the trick. Now if this is the case, right? I know these two relations. But what is x? AE plus r cos mu. Are you clear about this? AE minus r cos pi minus mu, right? AE minus r cos pi minus mu. But what is cos of pi minus mu? Minus cos mu. So A is this. But what is x from here? A cos E. Right? Now, in this relation, what is y? B sine E. Right? So you have relation 2, relation 1, relation 3. We have used this relation already. So this relation is of no more value. We are now using this relation y equal to b sine E and going to substitute it here. So b sine E whole square plus r square cos square gamma equal to r square. Now these are the only two relations left. How do I process this? I have r in terms of A. So cos E minus E is equal to r cos mu. Correct? Is this correct? So now I can easily define r square, this equal to b sine E square plus a square cos E minus E whole square. R cos mu square is substituted, right? This is the relation I will get. Now, if I use the relation and add it up from here, I would get r square is equal to a square 1 minus E cos E whole square. You can just do that. You can use this A and B relation as eccentricity, right? Because A and B are related by eccentricity. Correct? So if I substitute these relations, I get finally the R as A 1 minus E cos E. Right? If this is the case, I can substitute it here. Right? Now if your diagram is clear to you, I can rub it. Right? The whole thing you have to remember is we have drawn a circumscribing and inscribing circle of radius A and B respectively, and a point of ellipse is projected onto these circles to find true anomaly. Now if R is A 1 minus E cos E, I can substitute it here to get A cos E minus E is equal to A 1 minus E cos E cos gamma. So from here you would get, this A would get cancelled out, right? And you could now this make it as cos E 1 plus E is equal to cos mu plus E. So eccentricity, the true anomaly E, is related to existing orbiting parameters as this, which means other way around. If I know the eccentricity of the orbit, if E is known, E is predicted or measured, mu is known. What is the advantage? E is easy, right? It is a moving circular arm. This becomes very, very easy to find. That's the beauty. Elliptical equation is transformed into circular equation through true anomaly, right? And this is the most important and powerful derivation in orbital mechanics that you should be aware of. Now in mean anomaly, what did Kepler do? Kepler suggested therefore a function m0, wherein at t equal to t0 you have initial m0 as mean anomaly, the angle E. You can make m0 equal to 0 also, right, starting from elliptical plane. Then m will be simply n into t, right? N is mean motion. So simply this is like a omega, right? Which means the arm angle E can be found out by measuring the mean motion angle. So in circular orbit, you have n as root of gm upon a cube, right? And then your m is equal to m0 plus n into t. Say at t equal to t0, m0 is 0. Then it follows a linear relation. Advantage is sometimes this can be useful for transforming elliptical orbits into circular orbits and analyzing those equivalent orbits. Now, if this is clear, we have to see next important point of orbital transfer. So this is Earth. You injected something at this orbit. Now you want to expand the orbit size. Will you keep continuously firing the satellite through the rocket propellant? What is your estimate? That is not efficient. It will need lot of fuel to go far. If you want to say park something in Earth and then move it to Mars, do you think you would do something so stupid as continuously firing? You would need tons and tons of fuel which you do not have. So this uses something called as Hoffman Transfer. Right? It changes orbit in space by advantage of gravitational field and incremental burning velocities to minimize fuel consumption. Okay? To do this, there are two types where you want to send something outside your Earth orbit, right? Hoffmann Transport started before satellite actually for analyzing interplanetary transfers. So this is your nice sun here, right? This is a sun. This is Mercury, Venus, the inside planets, and then this is Earth orbit. Okay? My bad, I have drawn it too badly. Let's assume it is this orbit. Right? This is, say, orbit of Earth. So your Earth is here, somewhere in this window, and you want to fire something towards Mars. Okay? What would you do? Say at this point Earth and Mars are here. Will you follow this trajectory? No. What you do is, first you take your satellite and park it in a local orbit here. This is local parking orbit, like a conventional satellite, right? Now, in this maneuver, you will keep increasing the velocity by increasing its transfers such that this becomes escape velocity of Earth. And now, it no longer follows Earth orbit but solar orbit. But how so? The orbit that intersects the Mars orbit. You getting this? By that time you have calculated precisely that in delta t Mars would come nearby. In this window, as soon as it reaches Mars gravitational influence, it will break apart from this Sun orbit and will get captured into Mars orbit. So, what you have done is you have incrementally transferred between this orbit and this orbit by taking advantage of Sun's gravitational field. What if you want to, say, reach to Jupiter? There is this big belt of small rocks, right? I call it small rocks. Even astrophysicists sometimes call it small rocks. All these asteroids, and this is this big Jupiter. Actually, compared to Earth, it is this big. You use Mars as a flyby. So, you will not actually intersect Jupiter here. Your objective may be to intersect it somewhere here when it comes. When you come here, you actually take advantage of Mars, and as soon as you reach here, you give impulse to do a flyby. What does that mean? You are taking advantage of gravitational field of intermediate object Mars. So you are going in the Sun orbit. Sun is somewhere here, right? Now you are no longer in Earth orbit, but you are going in Sun orbit. Here comes the Mars. Compared to satellite's energy, Mars has a huge gravitational field. So you try to start squeezing in and form a local hypothetical orbit around Mars. Your objective is not to park there. You give an impulse. What would happen? The gravitational field of Mars will direct you, sling you in this direction. So some energy of Mars gravitational field gets imparted to this. And in flyby, your direction changes and you meet Jupiter here in this big delta T. But the main catch is in all this fanciness, the initial locations, the delta T and the slingshot locations are of precise importance. Which means when you launched and your Mars was here, you will never be able to catch it. If it was here, that's a problem. So you need a particular window, which is called launch window, in which the planetary positions are arranged so correctly that performing your Hoffman transfer, you have a guarantee of getting entrapped or reached in the particular gravitational field desired. So this is the entire concept of Hoffman transfer that was started and that he drove very beautifully. Now this has most practical application in satellite orbit transfer. Say again, this is the Earth, right? The geostationary orbit is at around r is equal to 36,000 kilometers from the center of Earth. Okay, roughly the number, right? So this is geostationary orbit. You want to launch a satellite from here. Will you launch it like this straight? Too much fuel energy. Will you even launch it like this? No. So you will launch it such that it first forms this small elliptical orbit or parking orbit. Then you will fire so that it goes into next orbit. In this orbit again you will fire so that finally you reach this orbit. This incremental sequencing of orbits from innermost to the destination is called Hoffmann Orbit Transfers, and it is used in satellites. So incremental Hoffman transfer. Now let's look at one hypothetical case. Let's say this is one first hypothetical near circular parking orbit. Let's call it P1. What is your objective? You want to go first into P2, highly elliptical parking orbit, and then your objective is to make it circular, final circular orbit. Sounds like a plan? This is our most optimistic strategy to minimize the fuel consumption, right? What does that mean? Moment you came to point A, right? Moment you came to point A, you want to change orbit which is circular to elliptical, which means the velocity properties here have to change so that new properties will make sure it forms this. Again, when you came here with certain VB, velocity again needs to be changed so that it forms a circular orbit. These are called inter-orbit impulses which you fire. So your velocity was 10 km per hour or 3 km per hour. You instantaneously fire your engines for a few seconds so that it goes up. There is hardly a drag in space, right? To 4. So here you get delta V1 and here delta V2. Your objective is to find these delta V's so that you can find out how much time I should keep my ignition on, and therefore how much fuel to carry from the ground for inter-orbit transfer. So let's quickly look at this problem, because this completes our theoretical background of inter-orbit transfer. So the first orbit which we had, I am going to draw it smaller now so that we can derive the derivation simultaneously. Let's find out the first delta V here, right? In circular orbit, so in P1, when it was here, what was velocity? Let's call it VIA. It was root of gm upon r, right? Now notice something which I am writing. In the elliptical orbit, this becomes perigee distance and this becomes apogee distance. So I can actually call it RP. But now, if I want to increment the velocity here such that it follows velocity of this, let's call this new velocity Vp, right? Vi, so VIA plus delta V makes it Vp. The impulse provided it the new velocity. What is the relation? Minus Gm upon Rp plus Vp square upon 2 is minus Gm upon Ra plus Va square upon 2. Conservation of energy. Conservation of momentum will tell me Vp into Rp is Va into Ra. Angular momentum. The advantage of these 2 points is the radial direction and velocity directions are perpendicular. So V parallel is 0. So because of this, the direct dot, the cross product can be obtained. That means VA is VP into RP upon RA. Let me substitute it here. So minus GM upon RP plus VP square upon 2 is minus GM upon RA plus VP square into RP upon RA square. Now I have everything in terms of VP, the unknown, right? Now let us rub these two equations because both equations are clubbed. So Vp square upon 2 comes constant out, right? On the right hand side you get Rp square upon Ra square minus 1. This comes here, Gm, right? 1 upon Ra minus 1 upon Rp, right? Now, how will I modify this equation? This will become Rp square minus Ra square, but A square minus B square is what? Rp minus Ra, Rp plus Ra upon Ra equal to Gm upon Ra Rp. So one Ra gets cancelled anyway and you get Rp minus Ra. So this minus gets out. So Vp is root of 2 Gm Ra upon Rp, Ra plus Rp. So this Ra plus Rp is nothing but A, right? So you have now the new velocity that you need to form this new orbit, and therefore because of this relation that initial plus delta is new, you get delta V required as root of 2 Gm Rp upon Ra, Rp plus Ra minus root of Gm upon Rp. This is the impulse, specific impulse that you have to provide to sustain.